you can use Lewis symbols to help model the valence electrons, and then from the symbols, then we can model the bonding in molecules, in covalent molecules. So the Lewis symbol, what it is it's just a model where you use the elemental symbol to represent the nucleus and all of what we call the inner electrons, and then use little dots to model the valence electrons. Okay, so if we try to repeat what was on that previous page with the hydrogen, it's like a little snapshot of the periodic table: lithium, sodium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Up here is helium, magnesium. You should be familiar with all these names and all these symbols: aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay, if I correlate that to this little chart that was just right here, and I'm going to draw Lewis symbols indicating, the valence electrons. So for hydrogen, of course, there's just one valence electron, and so the H is just modeling the nucleus. Helium, two valence electrons. Lithium has two inner electrons, so that would be modeled. The Li is telling me, okay, there's a nucleus and there's inner electrons, and then the valence electron, there's just one. Sodium, there's the nucleus, there's two levels of inner electrons, and then on the third level out, I have one electron. So you see the Lewis symbols look very similar, just the one dot. So that tells me this is going to behave chemically very similar to the others in the same group. Beryllium, there's two. Magnesium, there's two. And there's some question, should I put the two dots next to each other, or I'm scratching this off, should I put the two dots like this? It depends on the level of your model. I will accept side by side or on either side, as long as you get the two right. It depends on whether or not you're going to take your model to the level of the orbital notation, and that's the SPDF. We're not in this class. You may have in your pre-AP or your AP chemistry class, but we're not in this class. We're doing a very, very basic Lewis symbol. So for me, it doesn't matter, just as long as you get the right number. All right, so there's 3 valence electrons for both boron and aluminum. Carbon and silicon both have 4. I can model it like that. Nitrogen has 5, so I have to start doubling up. Same with phosphorus, oxygen. And again, it doesn't matter where you put the dots, as long as you you have to start, once you get past 4, you have to start doubling up, but it doesn't matter if the double is right here or on top or whatever. Okay, and then for fluorine and chlorine, we know there's 7. Okay, and I'm putting them in different places to show it doesn't really matter. I have the, 7, 2, 4, 6, 7. And then for helium, of course, there's only 2, and that's because that first level, the valence is considered full with 2. But for these other noble gases, they have 8 valence electrons. And so we consider normally, for most cases, a full valence or a satisfied valence is when you have 8 electrons in the valence shell. And helium, of course, is satisfied with 2. And since hydrogen is very, very tiny, when it bonds, it is satisfied with 2. And we'll talk more about that in a little bit. But you can see how the repetitive nature of the Lewis structures is telling me, okay, the outer electrons, the number of electrons on the surface of these elements is consistent down the groups. That's why within a group we have similar chemical behavior and similar what we call bonding behavior.